So looking at the fundamental equations for internal energy and entropy, do provide us some insight, but they don't really get us that much closer to, figuring out what ds dt or ds dp are, for, measuring the molecular parameters in the van der Waals equation. Okay, so the U and S fundamental equations provide insight but are not the most appropriate equations to use for a given system. Okay. And essentially, we can't really directly measure du or ds, right? Okay? And so what we could do, or what we can do, is instead we could transform our fundamental equations for U and S into other variables that are more useful. Okay? So what we're going to do is we can derive a more useful fundamental equation that is, a function of things like pressure, temperature, or volume directly. We could derive fundamental equations like that, and the method we're going to use to derive them is the method of Legendre Transforms. Okay. And by doing this, we could get equations that have canonical variables of measurable things like pressure, volume, and temperature. Okay? All right, and so Legendre transform can be a somewhat intimidating sounding name, but it's actually a fairly straightforward concept. Okay? Right? And so the way to think of it, a Legendre transform is just taking your original fundamental variable. So, like, say, for instance, U, your internal energy. And then what you do to it is you subtract off a conjugate pair of those variables. Okay? And doing this just gives you a new fundamental variable. All right, so that's the approach, or the concept of it, but it's going to make more sense if I actually just show you an example of one. Okay? And so if you remember, or let's take, for example, our fundamental variable of internal energy, and what we're going to do to it is we're going to subtract off the mechanical conjugate pair variables. Right? And so if you remember from the previous set of videos, that conjugate pair of variables was minus, the mechanical one was minus PV. Right? And I want to emphasize the sign here. That sign is important. Okay? And so what we're doing here is we're just taking the internal energy and we're subtracting off minus PV. Of course, you could rewrite that. The negatives cancel out and you get U plus PV. Alright, and so this U plus PV is going to give us a new fundamental variable but it's one that you've seen before, right? Because you should recognize at this point that U plus PV is just enthalpy. Okay? And so this definition of enthalpy is something you've seen before, right? But what we want to do now is we want to figure out the fundamental equation for enthalpy. Okay? And so what we're going to do is we're going to take the total derivative of enthalpy, so dH. And so the total derivative of enthalpy is going to be du plus the derivative of PV. All right? And so du, this is, for this, we just plug in the fundamental equation for internal energy. So we know that du is just equal to T ds minus P dV. So that's what du is. Now we're going to add on to it the derivative of dPV. So for this, what we are going to do now is we're going to take the product rule, since we have a derivative of a product. And so the d of PV is going to be P dV plus V dP. So here we just apply the product rule. All right, and so we see that here we get negative P dV. Here we get positive P dV. These cancel. And what we're left with is that the fundamental equation for enthalpy is just equal to T ds plus V dP. Okay? All right, and so this is the fundamental equation for enthalpy. All right, and so this was just an example of how to do a Legendre transform. But it's still, not... And so, to be clear here, what this fundamental equation is telling us is that H is going to be a function of S and P. So for enthalpy, the canonical variables are entropy and pressure. All right, and so that's different, right? But we still kind of run into the problem where one of our canonical variables, one of the things in that derivative, is still something we can't really measure. Okay? All right, and so, doing the Legendre transform to get enthalpy does provide insight, but it's not that useful. So what we're going to do is we're going to try out some other Legendre transforms. Okay. Before I go, I should also point out that if we took the partial derivative of h and compared it to the fundamental equation, what we would learn is that dH ds at constant p is equal to temperature, and dH dP at constant S is equal to volume. Okay, so that's, once again, just coming from comparing the total derivative to this fundamental equation. Okay. All right, so that the Legendre transform of taking U minus the thermal conjugate pairs gives us enthalpy, or minus the mechanical, I mean. Sorry, this was the mechanical. All right, so now what we're going to try out to see if we get something a little bit more useful is now we're going to take the Legendre transform of internal energy, but what we're going to subtract off this time are the thermal conjugate pair variables. And so here, the thermal conjugate pair were temperature and entropy. And this Legendre transform gives us what we call the Helmholtz energy. Right? And this is abbreviated commonly as A or F. You see both in the technical literature. Right? So they're both A or F are interchangeable. All right, and so that's the definition of the Helmholtz energy. Let's now take the total derivative of it in order to figure out its fundamental equation. So here we're going to have du minus dTs. du, once again, we know is TdS minus PdV. And then for minus dTs, we're going to get minus TdS minus SDT. The TdS's cancel, and what we're left with is minus SDT minus PdV. Okay? And so here, the canonical variables for Helmholtz energy are temperature and volume. And so that is now a new advantage. Now both of the canonical variables are measurables. Okay? If we did the partial derivative analysis on the Helmholtz energy, we would see that dA dt at constant V is equal to negative entropy, and dA dV at constant T is equal to negative pressure. Okay? All right, and so we see here that by doing this Legendre transform, we could define a new energy function in which the canonical variables are both measurables. Okay, now let's extend this even further. For enthalpy, we subtracted off the mechanical conjugate pair variables. For Helmholtz free energy, we subtracted off the thermal conjugate pair variables. And so the obvious next step is to just subtract off both. Okay? So now let's do subtract off mechanical and thermal. What you get? Pair variables. Yeah. And so if we do that, we get U minus negative PV minus TS. Okay? And here, if we cancel out the negative sign, we get U plus PV minus TS. U plus PV, that's enthalpy. And so here we get H minus TS. This difference, this is what we call the Gibbs energy. And this is abbreviated just simply as G. Okay. All right. And so if we take the total derivative of G, that's going to be dH minus dTs. For dH, from our first Legendre transform, we know that's equal to TdS plus VdP. And then if we take the derivative of Ts, we get minus SDT minus TdS. The TdS's cancel, and what we get is that the fundamental equation for the Gibbs energy is VdP SDT. Okay? And so G, the canonical variables are pressure and temperature. Right? And so, like the Helmholtz energy, for Gibbs, both of the canonical variables are measurable things. Okay? For the partial derivative analysis, dG dP, constant T is equal to volume, and dG dt at constant P, that's equal to negative S. Okay? All right, and so to summarize at least what we did here with all the Legendre transforms is we kind of defined a whole class of new functions that can potentially give us information about the molecular properties of our system in terms of macroscopic properties, things we could see with our own eyes or yeah. Okay? And so just to summarize, du, the fundamental equation is TdS minus PdV, and its derivatives are du ds V equals T, and du dV at T is equal to negative P. For the enthalpy fundamental equation, TdS plus VdP dH ds constant p is equal to t, dH dp constant s is equal to v. Helmholtz, dA is equal to minus s dt minus p dv, where dA dt is equal to negative s, dA dv is equal to negative p. And finally, the Gibbs energy, dg, is equal to v dp minus s dt. And this one's dg dp constant t is equal to volume, and dg dt, the constant p, is equal to negative s. Okay? Alright, and so these are all the identities, and the main benefit of doing the Legendre transform is for these new energies we developed, that their canonical variables are now in terms of measurables. But, we're still not quite near our goal of having ds dt constant volume, ds dp constant temperature, or ds v at constant temperature. We still haven't really figured out what those things are yet. But, we made some progress. In order to make the next step, now we need to start taking advantage of the properties of partial derivatives themselves.